Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So in this video we will look at histogram equalization, which is again a very useful pre-processing step, and this is typically used when the image is represented by a very few or very narrow range of pixel values, and it kind of shows up in the histogram when you see that histogram is sharply peaked, in the sense a lot of pixels have a similar range of values. And what this method does is to distribute the pixel values uniformly across pixels, leading to an improved contrast. Of course, the drawback with this method is that the method does not discriminate between signal and noise, so which means that you might end up corrupting the image quite a bit. So let's do some preliminary notation. So we assume some continuous intensity values, right? Let's just start with continuous domain. So R is the, let's just write this down. In this case, R is the intensity of the image to be processed, input image intensity, right? So we denote the pixel values in the input image by R. We also assume that R is in the range 0 to L. Okay. So that's typically assumed. We can always assume larger ranges if you want to. Typically 0 to L. Of course, when you go to a real image, we'll have to, where our values, pixels are discrete, etc. We will have to change a little bit, but at this point 0 to L. R takes on values 0 to L. Okay. So we can say that R equal to 0 is dark or black, and this is bright. So this keeps spilling over everywhere. So 0 is dark pixels, L is bright pixels. That much is right. Okay. So for given this R, okay, so we actually it's 0 to L minus 1. Sorry. 0 to L minus 1, which gives you L levels, correct? So L levels if you go to just integer values, right? But in this case we are going to assume a continuous intensity values. So for given this R, we want to find the transformation of the form S. Want to find a transformation of the form S equal to T of R. This is the transformation we want to find for 0 less than or equal to R less than or equal to L minus 1. Okay. So the idea is to it produces an output S. Okay, produces output S. And the assumption is that T of R is a monotonic increasing function. Monotonic increase in the range, in the interval 0 less than R less than equal to L minus 1. Okay. And if even after transformation 0 less than or equal to T of R less than or equal to L minus 1 for R 0 less than or equal to R less than or equal to L minus 1. So this is basically just a sanity check, right? If you can think of it, we want a 1-to-1 mapping. We want to go from R to S, and we should be able to come from S to R. So lower values of R should lead to lower values of S, higher values of R should lead to higher values of S, and the ordering should be preserved, right? Because we want dark pixels to be dark, bright pixels to be bright, except that we want improved contrast, and that we don't want, also don't want to go outside the range of values that you work with, right? So if the RGB pic, for instance, RGB images are between 0 to 255, when we do the so-called, we do this histogram equalization, we don't want suddenly have pixel values like 500 and all that. It has no meaning. So which is what this ensures. Okay, so it's a monotonic increasing function, and it also maps it into the same range. Okay, so that's the idea. That's the conditions for this histogram matching. Okay. So you can draw some of these functions. So for instance, something that is allowable, let's say, would be something like this, right? Where this is the L levels R and this is T of R. This is T of R. So that you don't have within this range, okay, within 0 to L minus 1. Right, you don't worry about it, what happens to it beyond these ranges, but within this range it's 1 to 1, right, and it's monotonically increasing. So it's similar. So you can't have multiple valued functions, right, functions that go suddenly flat, etc. We can't have functions like that. So that much is understood. Okay. So what we want to do is to estimate a transformation of the pixel intensities from from the source image, so that the pixel intensities are uniformly distributed in the finally the synthesized image, right? Where the which is what we call the synthesized image or the transformed image, right? So you want to transform the pixel values in your input image according to some function, smooth function, so that you get another new image, and if you plot the histogram of the pixel values there, that corresponds to a non-uniform distribution. Okay, so there is a fundamental result from probability theory that the PDF of the transformed variable is given by this expression right here. Okay, right, where R is your source. The subscript R refers to your source image, that is the original input image, and S refers to the image that you are synthesizing using this transformation function. Okay, so why I am suddenly using PDF, right, probability density function. So where did that come from? So like I said, if you plot the histogram of pixel values, okay, and then you normalize each bin in that histogram by a total number of pixels, what you get can be approximately considered the PDF of the pixel distribution in that particular image, right? PDF of the pixel intensities in that particular image, not the pixel distribution. I mean to say PDF of the pixel intensities in that image. Okay, so it's actually an empirical estimate of the PDF. It's not the true PDF, empirical estimate of the PDF. So what we are trying to do is to create from that PDF. We are trying to create a uniform PDF. So just to show you what is uniform PDF, which I already did in the last slide. Let me just create a new one. So what is the technique for doing that? The idea is the following. So if we think of, let's say, PR and PS, right, to correspond to probability distributions of intensity values R and S are intensity values. Okay, they correspond to probability distribution of intensity values. You can think, whenever I say probability distribution on PDF, think histogram. It's fine. Okay, just for understanding. So you can use R and S correspond to the subscripts correspond to the intensity values in two different images. At this point, let's just assume they are images, right? So the fundamental result from probability theory is that P subscript R and T of R are known, right? So if you know PR of R and T of R, and also that TR is continuous and differentiable over the range of values of interest, right? So then the PDF of the transformed variable S. So R is our original, let's say in our case given image, we denote it by R, right? So PR of R corresponds to its histogram from which we derive its empirical PDF. And if we know the transformation function T of R, we know that it's a continuous distribution. Okay, then we can write PS, the distribution that we obtain of the transformed variable, as PSC subscript S of S is given by this expression. Okay. Now, if you're wondering why it comes out this way, why this is possible, is because we always remember the relation is that S is equal to T of R. So we have a function T, capital T, which takes our input image pixel by pixel, its intensity R, and outputs an S. For every pixel intensity R, it outputs an S in the new image. Right. Now, if T of R is continuous and differentiable, then it is possible to estimate the target or the synthesized pixel distribution. Okay. Now, we can do this by considering S is equal to T of R, and we contend that the T of R, the function T of R that does this is nothing but this cumulative probability distribution. This is the cumulative CDF, cumulative distribution function. Okay. Cumulative distribution function for any probability distribution, let's say, is nothing but if you have P of x dx 0 to x. Okay. That's how you define the cumulative probability distribution. That's this right here. So the transformation that enables, so if you consider this transformation, this is again we can show that this is continuous and differentiable for all ranges, all pixel values of interest. Okay, and if you put it in this form, L minus 1, again it corresponds to, there are L levels, correct? And so we can write it in this form. So this is the function. We are claiming that this function does the job for us. Okay. So this function is what makes your P of S into a uniform distribution. Okay. So we can prove that, because there are several things. How do you know that it's continuous and differentiable? You can prove that because you know our PDF. If we know that from there we can show that this is actually true. So from here we can actually calculate ds by dr. Okay, we can actually calculate ds by dr, from which we can calculate dr by ds. It turns out if you do a lot of algebra, okay, so we will end up getting Ps of S to be 1 over L minus 1. Okay, so this might seem a little bit rushed. So let me let's take out the clutter, okay, and so let's understand what we are trying to do. One second. Okay, so we started with this, given an image, we know that its PDF or histogram is denoted by PR of R. Okay. Now we want to find a T of R which gives you S. So for every pixel intensity R in the image, source image, we put it through this function T and it gives us an S. Okay. And from the basic results of probability theory, we can show that this is true, that P subscript S of S, that is the probability distribution of S, is given by this function. Okay, this is under the assumption that this T of R is continuous and differentiable. Okay, now the special case of T of R, which is given right here, this is what we looked at, L minus 1 0 to R PR W dW. Okay, W is just a dummy variable, PR is the input image pixel values distribution, pixel intensity probability distribution is P of R. This W is nothing but the dummy variable of integration. Of course, this integral itself is nothing but the cumulative distribution function. Okay, and L minus 1, where L is the number of intensity levels that are allowed in the image. So for instance, you take an RGB image, all the values go from 0 to 255. So you have 256 intensity level. Now, if we use this particular T of R, okay, then we can show that P of S, follow the algebra, P subscript S of S is nothing but 1 over L minus 1, which is the uniform distribution. Okay, and this is just a bunch of algebra. I urge you to walk through it. But the idea is we are trying to find out a transformation T of R, which will give us the uniform distribution in the synthesized image. Okay, and it turns out this transformation yields that. Okay. So again, the idea here is once again to make the pixel intensity values uniformly distributed in the synthesized image. So this is the algorithm or the intent behind histogram equalization. Of course, you can put in you can try different forms of this function, but typically what you want to find out is what you want to estimate is that that the synthesized image has a uniform distribution. Okay. So the point is, how do you figure out T of R? Okay. What is this T of R that will work? Okay. The idea is that the intensity of an image can be viewed as a random variable. So which means that we can say that its histogram distribution is nothing but its PDF or the probability distribution, right? So then we can talk about probability distributions of the input image and the transformed image. So P subscript S of S denotes the probability distribution or the histogram distribution of the synthesized image, and P subscript R of R corresponds to the input image. And there is probability theory, if R and S are related by the smooth transformation, then the probability distributions are related through this expression. So this is nothing but the multiple dimension. This modulus dr ds is nothing but the Jacobian of the transformation, right? So what is this transformation that will work? So generally the most common transformation is this. T of R is given by this expression. Of course, in this integral, W is nothing but a dummy variable of integration. So it's basically the input image probability distribution function which is there. This integral itself is nothing but the CDF, cumulative density function. Okay. Now from here we can actually calculate ds by dr, and from there dr by ds, and you substitute it in this formula over here, and you will be able to see that Ps of S is 1 over L minus 1, which corresponds to the uniform distribution. So which is what we want, right? We want the uniform distribution for the transformed image. So if we let the transformation function to be L minus 1, a factor multiplied by the CDF of the input image PDF, then we get the following output. That is basically the output image has a uniform distribution. Okay. So how we saw this, and we look here. So how do we actually do this, right? So calculate the CDF of the cumulative histogram, as we call it, of the original image. So the input image is F. So we calculate the CDF of the cumulative histogram. Okay. So number of the levels in the image is L. So we typically have 256 levels. Okay. And this is typically how you would calculate the probability of a particular level K. That is, calculate the number of pixels in that level K divided by the total number of pixels, which is nothing but the image size. Okay. And the way you would calculate SK, which is basically the synthesized pixel value, is T of RK, which is given by this expression. So you would do this in a numerical fashion, right? So the motivation here, like we talked about, is to assign equal probability to all pixel values. Okay. And it turns out that the transformation function is nothing but the CDF of the pixel values of F. Okay. So given any pixel value, you can, in the source image or the input image, we can calculate the transformed pixel value. Okay. So we can, of course, we just showed that the transformations obtained this way. Turns out that S's are uniformly distributed, and so that gives us the neat picture. And show the computations. So you just calculate the CDF or the cumulative histogram of the original image, right? The number of levels in the image is L, assuming, right? And then for every level in the image, right, every RK, where K is the level in the image, you can calculate what the corresponding S is, and then assign it to that value. Okay, so that's it. So once you are done with that, then you can then you have the new image actually done for a discrete image. How is it done, right? So I'll wipe out the existing things here so that you can see clearly. So how does it work for in the case of a real image, right? So for the computations, we know that in a lot of cases there is a finite number of levels in the image. So basically we say capital L is 256, right? and the CDF or the cumulative histogram of the original image F, right? And I think I must have used the wrong terminology here. We'll just use CDF. How do we calculate the CDF of the F, input image F, right? So we can calculate the probability for a pixel to be at a particular level K given by RK, right? The intensity value corresponding to level K is given by RK, and that probabilities depend nothing but the total number of pixels with that in that level K number of pixels in that level K divided by total number of pixels. M comma N, M times N basically is the size of the image, right? M rows, N columns. So that's how we have, that's a total number of pixels. So we can always then find out Sk as this finite sum. Okay. So the integral is replaced by a summation in the case of discretized image, right? So this process is is implemented for histogram equalization. So here are some examples, right? So this is the original, this is an MRI of the brain. So you can see the image on the left, it's uniformly dark. There are some structures inside that you can see, and outside, of course, the skull. But once you do the transformation, this is just a histogram equalization, you can see that their structures are much more visible. There's a much better contrast compared to here. Of course, it looks slightly more noisy, and that's an issue, but still you get better contrast. Here too, there is some dark. See, this region is slightly dark. This region is slightly brighter, but that is much more apparent here, along with all the other artifacts which are shown, artifacts or structures in the brain that are clearly shown here. Okay, so once again, if we go, and that has much better contrast than the others. So for instance, in this case, this is a slice of an MRI of the brain. As you see, the top row and the bottom row, the left hand picture. Once again, I will remove the markings. So if you look at the top row and the bottom row, you see that the left column is nothing but the raw image, and the right column is the histogram equalized image. You can see that it becomes appears somewhat slightly noisy, but you see that while the image on the left, both of them are uniformly dark, you can see that on the right hand side there is a contrast obtained between different regions of the image. Okay, so you might find it noisy because the background has gotten a little bit noisy, like I said, because the algorithm doesn't distinguish between bright and dark regions, right? So it does, in the sense, what I mean by bright and dark regions, it doesn't distinguish between noise and real signal. So in this case, this dark region is just noise in this, right? Because it's just background, there's nothing there. There's just a head in the middle. So, but then it doesn't know that, so it just spreads pixel values everywhere. So that is the only issue, but other than that, you get excellent contrast. So in many cases, histogram equalization might not be appropriate, okay, or we will have a completely different idea of what it means to modify the histogram. So for instance, let's consider, in this current scenario, a lot of deep learning techniques are being used for medical image analysis, right? So our machine learning techniques are used for it. But let's consider a situation where your data is drawn from, your image data is drawn from multiple scan centers, etc. Okay. So one pre-processing technique there, in order to account for the difference in dynamic range of these pixel values from each of these centers, you can do histogram matching. So in this case, the idea is not to turn everything into a uniformly distributed pixel value image, but rather you have a target histogram. Okay, a target histogram is given, which is kind of considered ideal. And then what you do is you try to match all the image histograms to that target histogram. Okay, so instead of the uniform distribution, so in the previous case we saw when we do histogram equalization, the uniform distribution was the target histogram or the target PDF. In this case, you might have an ideal image. You might actually have done an averaging of a bunch of images which had very good contrast, very good SNR, etc., and derived a PDF from there or a histogram distribution from there, and you want to match everything to that. Okay, that's the other scenario where this histogram manipulation is done. So that process is called histogram matching. Okay. So here we'll just clarify notation once again. This PR subscript R is the input image distribution. Once again, we'll start from the continuous distribution, and then we can go to the case where in the images, the pixels are discrete and have discrete values, etc. And P subscript Z is the specified target histogram. It's a target histogram shape, if you want to call it that. I've used the term histogram distribution. Okay, might not be correct or commonly used, but that's for the case of just for the sake of understanding we use it. Okay, or pixel intensity PDF is another terminology. So the P subscript Z of Z is given, P subscript R of R can be estimated from the input image. Okay. Now what we can do is to do this transformation, yes, which we have seen. So this is T of R. Okay. Take this and we do the cumulative PDF calculation to get S. Okay, so this is T of R. Similarly, with the P of Z, P subscript Z, which is also given, this is the target histogram, we do a similar transformation. Okay, so now what we have to identify is that these two are the same, right? This should give you the same values, provided we have this, that G of Z, since again, just to clarify, this V is just a dummy variable, right? So we can say that G of Z equal to S, which is equal to T of R, right? This is true. Correct? So the Z that we are getting then must satisfy the following condition. Z is G inverse of S, correct? This is just from this equation, which is G inverse of T of R. Okay. So we can, if we back one more time, in the continuous formulation, we can estimate P of this. This is given. This is from the image. We can estimate this from the input image, right? And we can use Pz of Z. We have, this is given. Pz, in this case, P subscript Z of V is given, but V is basically just a dummy variable. So once you have P subscript Z of Z, we can also calculate G of Z. So T of R and G of Z can be readily calculated. Then all you have to do is estimate G inverse of S. Okay. And so then we are done, correct? So for every S value, we calculate Z, which is G inverse of S. Okay. So, but estimating G inverse is not an easy task, right? It's a computationally, analytically difficult task to do. But when you are working with discrete quantities, which you will see in the next slide, this is not a problem. Okay. So then what we did, like we did in the previous time, we convert this continuous result into its discrete form. Okay. So when you say discrete form, it means that you work with the histograms of the image, empirically determined histograms of the images and the target histogram, right? That's what we have. So how do we do? So in the case of, okay, so we'll go on to the next technique, which is histogram matching. Very similar to this, only that now we don't make it into a uniform distribution. When I say make it into a uniform distribution, I mean that we have an input image, but our target is not to get to a uniform distribution after processing, uniform distribution of the pixel intensities after processing. Here we are given a target histogram. Okay, we given a target probability distribution of pixel, a target PDF, right? So go through the algorithm. This is the discrete formulation. In the continuous formulation, this discretization, we calculate Sk from the input image for all the L-1 levels in the input image. So once again, if the target histogram has Q levels, we calculate the same for every Q, right? And then how do we invert this G inverse, right? How do you do that? Okay, that's the tricky part, right? So from the, how do we get the Z of Q from the inverse? Okay, so there is no need to calculate this so-called inverse, because what we do is basically we are using, when we deal with these intensity levels, either Q, L minus 1 intensity levels, right? Is that they are discrete and they are integers. Okay. So we can calculate all possible values of G. Okay. So calculate all possible values of G, and these are rounded to the nearest integer value in the range 0 to L minus 1, and you put them in a lookup table. And then for a particular value of Sk, we look up, to the closest value, right? So that's all there is to it. Right? So for every possible value of Zq, you calculate G of Zq, it's not a problem. Z subscript Q for every Q level, every Q, we calculate this. So then from Z1 to let's say 100 level, Z1 to Z100, you can calculate. And for a given Sk, find out which is the closest and you can just do a nearest neighbor match. Okay. So this is the typical approach. So we don't have to invert any function, but just use a lookup table. Okay. So for a discrete case, this is the case where you are actually provided the histogram, not a continuous function, etc., but rather a discrete function. Right. So what we do is we calculate the histogram of the input image and the histogram equalized pixel values, right? S, we calculate S, right? So we do S case as we want in the range 0 to L minus 1. Okay, we do this, right? So, so we compute the cumulative histogram of the target, right? G, which is basically nothing but GZQ. And that goes from where Q goes from, once again goes from 0 to L minus 1. Right? For the target histogram, we do the same thing. So we always round the values of G to the nearest L minus 1, nearest 0 to L minus 1. Right? Store the rounded values in a lookup table. So for every value of Sk that we have, we find the closest. We find Z subscript Q so that G of Z subscript Q is closest to the S. That's all we do. So for multiple matches, we use the smallest value. Okay. So that's it, then your mapping is done, because we have every equalized pixel Sk is now being mapped to the corresponding pixel with value Z. That's all we want. Right? So we have now mapped from our input to S to Z. Okay. So see the intermediate step of equalizing the input image is conceptual, right? And because we can skip it by doing a cumulative, but we won't get into those details. But this is the way, right? This is the way to do it. So given these input values, given the input values, given the input image, you calculate its histogram, you calculate its equalized histogram. Then you do the equalized histogram for the target histogram given, and then you map them. Okay. So now that way you are now mapped to Z. That's from your input you have now mapped to Z. Okay. So this is the what I call the histogram matching step, which is used as a pre-processing step in many applications. So right now there are implementations of this available in MATLAB and other open Python, etc. You feel free to use them, but internally this is what is happening. Okay, so the next videos we will look at edge detection, etc. But this is all for histogram matching. Thank you.